So in this video, we're going to kick off our unit on thermodynamics by discussing the concept of spontaneity. So this word here is pronounced spontaneity. Okay? So where does this fit into the larger picture of what we've been studying? So far, we've discussed how fast reactions go. Okay? So this was our unit on kinetics, where we talked about rate laws, and reaction rate, and order of reactions, first order, second order, etc. And more recently, we've talked about how, I guess we would describe it as, far reactions go. And this is in terms of equilibrium. Like when we use the value of K and whatnot, does it favor the products, does it favor the reactants, how much? Which side are they favored? In this unit, thermodynamics, we're going to try to decide, or we're going to try to figure out how these things are related to energy. Because we know that all reactions involve changes in energy. And will those changes in energy allow us to predict how fast reactions go, or how far they go, and vice versa? That's what we're going to discuss. So just a quick little review first. Enthalpy. Okay? Remember enthalpy, delta H. Okay? This is the change in heat in a reaction, okay? So remember, we used calorimetry, Q equals mc delta T, to figure out the amount of heat that's given off in a reaction, either gained by the system or gained by the surroundings. And then we learned if you wanted to calculate delta H notch of a reaction, that was equal to Q over the moles of the amount of compound that was being involved. And if we knew the products and the reactants, we could also figure out that delta H naught of reaction is equal to H of products minus H of reactants. So those equations hopefully look a little bit familiar to you. This type of equation and relationship is going to pop up a lot in this unit, but with two new quantities, not enthalpy. But just a refresher, enthalpy is measuring the energy transferred in a reaction. So this is the energy transferred in a reaction. So how have we modeled that? Well, let's say we have a reaction of, compound A turning into compound B. We know that for any reaction to occur, okay, let's just say this is A here, energy must be added. If it's endothermic or exothermic, it doesn't matter. You always have to add a certain amount of energy. And that amount of energy, okay, E sub A, is called the activation energy. Okay? In this case, the activation energy would be 160 kilojoules. That's how much energy would need to be added for this reaction to occur. Once that's occurred, we've gotten up and over the hill. So A will hit up here, which is called the transition state. Okay. And in the transition state, remember what's happening is the reactants bonds are breaking. So maybe we have A bonded to A, and this bond is getting broken. And then when that happens, over here, bonds are being made or formed. And so once those split, these A bonds split apart, maybe that's what leaves us with compound B. Any reaction, like we said, needs energy to start it, but we can also figure out, is it endothermic or exothermic? So here, since the amount of energy that we have at the end, this is H of products, and here's H of reactants, we know based on this relationship we can figure out the delta H. Since H of products is 160 minus H of reactants 80, the delta H of this reaction is positive 80. Since it's greater than 0, that means it's endothermic. Okay? We also know if delta H is less than 0, it's exothermic. And what would that curve look like if we redrew it? Okay? We would have the final energy down below the initial energy. So that's a little refresher on what we've talked about. We're going to tie that into some new concepts going forward. First, specifically talking about reactions that are spontaneous. So we need to know, what is the difference between a reaction that is spontaneous versus a reaction that is non-spontaneous? Okay? So this word, spontaneous, what does that actually mean? Well, if you think about it just in an English sense, the word spontaneous, if someone is spontaneous, they just kind of do stuff spur of the moment. They just kind of happens. They just, hey, you want to go to the movie right now? And you're like, boom, yeah, sure, let's go right now. There's not much else needed for the person to do the action. It's the same thing with reactions. So a reaction is spontaneous. If it's spontaneous, that means it occurs without outside assistance. Okay? You don't need to change anything special to make a spontaneous reaction occur. All you need is the activation energy. Okay? That's all you need. If you add the activation energy, the reaction will happen right away. So what are some examples of spontaneous reactions? Well, let's talk about a non-chemical example. Let's say you have an egg, okay? And you're holding the egg and you drop it. When that egg hits the ground, it's going to splatter. When you drop it, it is spontaneous. There's nothing that's needed to make that egg splatter besides you letting go. It's going to happen, okay? On the other hand, non-spontaneous reactions, okay? Non-spontaneous reactions, okay, require outside assistance, okay? And what that usually means is a change in conditions, okay? A change in conditions. So you need to change the temperature, you need to change the pressure, you need to change the volume, or do something differently, okay? Let's think about the egg example here, okay? An egg that's broken on the floor, okay? By just leaving it there, it's never going to go back up and turn back into an egg by itself. That's never going to happen. That's a non-spontaneous process. It's not spontaneous. Okay? You would need to have some special outside assistance. In this case, maybe some glue and some paper clips. Okay? A lot of different stuff in order to take that broken egg and turn it back into a whole egg. Okay? How about a more chemical example? Let's say you take water, okay, or ice, H2O, solid, and you put it in a room where the temperature is like 50 degrees Celsius. Well, if you leave that ice out on the table, over time that ice is going to turn into a liquid water. It's going to melt, okay? This is a spontaneous process. You don't need to do anything to the ice specially for it to melt. It's going to melt as long as the temperature of the room is greater than the melting point of the ice. On the other hand, let's say you just take water, H2O, in a cup and you put it out on a table. Will it ever turn back into ice if the room is 50 degrees? No, not at all. That's a ludicrous idea. Water doesn't just turn into ice unless you change the conditions. So if you put the water into a freezer, for example, then this becomes spontaneous. But otherwise, it's non-spontaneous. Okay? The other word that we need to be familiar with is reversible, which we've already talked about. Okay? Reactions that can go both ways are reversible. Spontaneous processes, okay, are non-reversible. So think about it. Egg dropping to the floor, we can't just reverse that and have the same thing happen. It doesn't work that way. Spontaneous processes are non-reversible. Okay? So if you look at these two examples here, you have a rock on a hill. The question is, which of these is a spontaneous process and why? Well, the rock just being on the hill, if you just let it go, it's going to fall down. It's not going to require any outside assistance. So this would be a spontaneous process because it does not require outside assistance. On the other hand, getting the ball to roll up the hill, that's going to be non-spontaneous. The ball's not magically going to roll up the hill by itself. It's going to require some outside assistance. In this case, Shar, with some nice beautiful hair here, okay, is going to need to come in and push this ball up the hill in order for it to happen. It's not going to happen by itself. Okay? So, what's so special about that? Well, where thermodynamics comes in, which is what this unit's going to be all about. Okay? If we connect it back to what we've been talking so far, we've been discussing about speed of reactions and how far they go. Thermodynamics is going to tell us the direction, meaning forward or reverse, okay, and extent, meaning how far a reaction goes, but not speed. So thermodynamics will not tell us anything about how fast a reaction will occur, but it will tell us what direction and how far it will occur, and we'll be exploring that over the next 2 weeks.